Hello everyone. Today in this video we'll be covering basically what the types of energy braking techniques are to follow reaction mechanism. Now we have already studied in the different classifications of organic compounds and in their chemistry. We have studied that they follow a certain reaction mechanism. Now what we'll be studying over here is the types of bond fissions that take place that lead to certain reactions taking place. Now these reactions or these fissions, these types of fissions occur only in covalent compounds. Keep that in mind. There are two types of fissions, heterolytic fission and homolytic fission. Now we'll be doing both of these in this video. Heterolytic fission occurs when shared electrons of a covalent bond are transferred to one of the bonded atoms, and this occurs in polar covalent bonds. So what exactly happens is that both of these electrons move towards the more electronegative atom. So we know that whichever is the more electronegative atom has the partial negative charge, and whichever is the less electronegative atom that has the partial negative charge, partial positive charge. So now both of the electrons would go to this and we would draw a curly arrow, right? That leads to the atom B of this compound getting an extra electron. Therefore, it would form this anion, and that would lead to atom A getting one less electron. Why? Because it has a bonded electron. It has contributed an electron. So therefore, that would lead to this cation A. Now, what we are trying to deduce from here is that heterolytic fission leads to a compound being broken into ions. So now let's look at some examples. If we have HCl, which is hydrogen chloride, if we break that, heterolytically what will occur is that we would have this. Obviously we know that chlorine is the more electronegative atom and hydrogen is the less electronegative atom. So what would occur is that both of these electrons would go to the chlorine and we would have the chlorine minus ion, and what that would look like is that the 7 valence electrons of chlorine would be there and we would have the 1 hydrogen valence electron also. And then the H plus ion would be like this, right? So, and now what if we have a slightly more complex organic compound, for example the one that I've drawn over here. Now over here what will happen is that this is one entire portion of the compound and this is another, right? So when we affiliate the delta negative and delta positives, we will do it according to that. Chlorine is quite electronegative, so it is definitely more electronegative than this non-polar portion of the organic compound. So when this heterolytically breaks up, both of the electrons go to the chlorine and it forms the chloride ion, but it also forms this entire ion. Now this ion goes into a classification of ions which are called carbocations, and there are quite a number or types of carbocations which are covered in previous organic chemistry chapters, right? So this is basically heterolytic fission. Now what occurs in homolytic fission? In homolytic fission, the shared electrons of a covalent bond are equally distributed in the atoms, and it occurs in non-polar compounds. Now what happens is when it occurs, when this homolytic fission takes place, the products that are formed are called free radicals. Okay, now free radicals is a term that you must have come across in free radical substitution reactions of alkanes. So keep in mind that this is one and the same thing. So for example, you have a chlorine molecule, right? Now this is a non-polar compound because they are equally electronegative. So the two electrons would break up equally. So this electron would go to this one and this electron would go to that one. So one will go to each of them, and we will not draw a full arrow. Keep in mind that I have not drawn a fully formed arrow. I have drawn this partially formed arrow, which is called a fish hook. Okay, so this partially formed arrow is called a fish hook in layman terms, obviously. So keep in mind, for heterolytic fission we use a fully formed arrow. For homolytic fission we use a partially formed fish hook. Okay, and that shows the movement of one electron. Now when each of them get one electron, what occurs is basically that they form these radicals. Okay, and radicals, free radicals, are a species with an unpaired electron. Keep that in mind. Okay, so they are unstable and they have an unpaired electron. So now let's move on. Now keep in mind that let's just go back to this reaction for a little bit. Okay, now if you remember, in free radical substitution reactions we used to have a condition for breaking the chlorine covalent bond. UV light, ultraviolet light, must be present because energy must be provided for this reaction to take place. So keep that in mind also. Now lastly, we'll be doing the differences between homolysis and heterolysis. Heterolytic fission and homolytic fission can be termed as homolysis and heterolysis also, as their processes. Now, heterolysis it takes place in polar covalent bonds, while homolysis takes place in non-polar bonds. Heterolysis occurs readily during collision, meaning energy does not need to be provided for it to occur, but homolysis needs energy in the form of UV light, for example in free radical substitution. Heterolysis In heterolysis, the shared electrons are unequally distributed, so a fully formed arrow. In homolysis, the shared electrons are equally distributed, they form free radicals, so by a partially formed fishhook. And in heterolysis, they result in the formation of ions due to the change in electronegativity, and in homolysis, they result in the formation of free radicals. So keep these in mind because these terminologies of processes are quite important in understanding reaction mechanisms. Thank you.